We're now going to look at variations on the Claisen condensation reaction. And these are going to get a little bit tricky to kind of keep track of. So, if things are blowing your mind at this point, they're really going to blow your mind now. And the first one we're going to take a look at is what's called an intramolecular Claisen condensation. So we saw intramolecular aldol condensation. Now we're going to look at intramolecular Claisen condensation reactions. And these types of reactions have a specific name called a Dieckmann condensation, named after Dieckmann, who discovered these types of reactions. All right, so um, intramolecular aldol condensations are a little bit tricky. Intramolecular Claisen condensations are trickier because, again, you're losing that ethoxide and reforming a carbonyl in the process. So let's take a look at an example. Here we have a diester. We're treating it with a base. And if we think about what's going to happen here, obviously we have alpha hydrogens on either side, and so we can deprotonate that alpha hydrogen, one of them, to form our enolate. So this is the enolate. Of course, we could form it on either side, doesn't really matter, but I'm showing it on the right side. And so now that enolate is going to attack the other carbonyl on the left-hand side. And the easiest way to do this, again, for me, is to number 1, 2, 3, 4, 5, 6, so that, and I always start at the carbonyl that is going to get attacked. That's carbon number 1. So I have 6 carbons, including the enolate carbon, so I draw a 6-membered ring. And of course we can number 1 through 6, and on carbon number 1, what do I have? I have an ethoxy group coming off, and I have an O minus coming off. On carbon number 6, I have the ester coming off of it. The next step, as we've seen with Claisen condensations, is an elimination step. So I'm going to reform the carbonyl, and I'm going to kick off the ethoxide. And the result is that beta keto ester. Now, it's a cyclic beta keto ester, and that's kind of the cool thing about these types of reactions. Again, the same procedure follows as typical Claisen condensation reactions. I'm generating an ethoxide. I have an alpha hydrogen that I can remove to form my anion, my resonance stabilized anion. And now if I, and then the reaction stops there, right? So again, equilibrium is favored toward the starting material until I get to this stage where deprotonation occurs, and now I'm driving the reaction toward product formation. And at this stage now the reaction is complete. I now have to acidify to generate my neutral species, and I get my cyclic now beta keto ester. So intramolecular Dieckmann condensation reactions are ways of producing cyclic beta keto esters. So here's a reaction where I have two esters. I treat it with sodium ethoxide in THF followed by an aqueous acidic workup. I can see that the alpha carbon is going to attack the carbonyl. I form a 5-membered ring, and the result looks like this, beta keto ester. Work on practicing drawing these structures, right? So I'm going kind of fast because we've seen these types of reactions before, but if you're having a difficult time and struggling with how things come together, slow it down. Show the enolate forming. Show the enolate attacking the carbonyl. Draw the resulting oxoanion, the tetrahedral intermediate. Then show the elimination step, and follow your progress until you start to kind of get the hang of actually seeing how things are going to come together. Now, one thing that I mentioned previously that we're going to think about now, kind of to complete this type of reaction scheme, is that if you have noticed by now, you can hydrolyze the ester and decarboxylate the resulting beta-keto carboxylic acid. So if I take the product that I just formed up above here, this cyclic beta-keto ester, I treat it with sodium hydroxide and water, followed by aqueous acidic workup to get my carboxylic acid, and then I heat this up. I lose the carboxylic acid, and I generate ketones. So I'm losing that entire carboxylic acid structure, the entire ester structure altogether. Retrosynthetically, this can be challenging, and so again, you have to think about, if you're asked to make a ketone, how do you make the ketone? What are the starting materials? Always retrosynthetically add a beta carboxylic acid to it, and then make it into an ester, and so on and so forth. Let's look at another type of Claisen condensation reaction, and that is a crossed Claisen condensation. We've seen crossed aldol. We now are going to look at crossed Claisen condensations. And of course, these have the same issues as crossed aldol condensations in that if you put two esters together in solution with a base, you're going to get a mixture of products. And again, we can use an enolate, we can use an ester that has no alpha hydrogens with an enolate. And so esters that have no alpha hydrogens are benzoates, derivatives of benzoates. These are benzoic acid with an R group, so the alkyl benzoates they're called. Also, we could use formates where you have an ester, the ester on one side, and a hydrogen on the other side. So we can't form an enolate with formates as well. And the last one that you'll often see are carbonates. So alkyl carbonates, where you have a diester attached to the carbonyl. So we'll take a look at an example of each one of these, right? Here we have an ester. We treat it with LDA to form our enolate of the ester, and then we can treat that enolate with another ester that can't form an enolate, namely a formic. So this is methyl formate, it's called. And of course, we form the enolate of the ester on the left. That enolate can attack the carbonyl and generate our tetrahedral intermediate. We then get a collapse, reforming the carbonyl and elimination of the alkoxide, the methoxide. And then once we acidify, we get this structure, this beta-keto ester. And notice with this beta-keto ester, I can treat it with sodium hydroxide and water, followed by an aqueous acidic workup and heat, forming my beta-keto carboxylic acid, and then elimination, decarboxylation. And it's a great way of making aldehydes. Notice this is a way of making aldehydes. So if I take formates and treat it with the enolate of an ester, I can certainly make beta-keto esters, but if I hydrolyze and decarboxylate, this will lead to the formation of aldehydes. Alright, so let's take a look at an ester, or the enolate of an ester, reacting with a benzoate. Here we have ethyl benzoate, followed by an aqueous acidic workup. And if we think about how to draw the structure of that product, I want you, at this point, you should be able to pause the video and see if you can draw the structure of the beta-keto ester. So that's what I want you to do. I want you to pause the video and see if you can draw the structure of the beta-keto ester that's formed from these two things reacting together. Okay, let's see if you have it. So the first thing you should do is draw uh, the backbone of the benzene ring, and then add it to the alpha carbon of my ester, the enolate that formed, right? And you get a structure like that. So hopefully you were able to draw that correctly. Of course, now we can add sodium hydroxide followed by that aqueous acidic workup and then heat to form the beta keto carboxylic acid and then decarboxylate that carboxylic acid. So let's pause again and see if you can draw the product. Okay, so let's see what that product looks like. This is the structure. And this is a way of making phenylketones. We saw how to make methyl ketones prior. Now we know how to make phenylketones with um, benzoate, ethyl benzoate, methyl benzoate derivatives. And the last one is reacting an ester, the enolate of an ester, with carbonate. Here I have dimethyl carbonate, so I treat the ester with LDA to form my enolate. The enolate then reacts with the carbonyl of the carbonate, the dimethyl carbonate, and then upon acidification, we get a beta diester. So let's again see if you can draw the product of that resulting structure. All right, it looks like this. So a beta keto ester. And upon hydrolysis, I'm going to get a 1,3 dicarboxylic acid in this particular case, which can undergo decarboxylation. And let's see if you can draw that product. And the product looks like this. So hopefully you're able to draw the product. If not, come see me. I will certainly help you out. This isn't an easy thing to do, but it's when you use carbonates, you can make carboxylic acid. So another way of making carboxylic acid derivatives. So we know a variety of ways of making carboxylic acids, and this is simply adding to our arsenal. And now you see kind of a broad spectrum of aldol condensation and Claisen condensations and their resulting products. And hopefully with practice you can figure out how to draw those structures.